at lunch. Just a quick short survey. We'd love to get your feedback on them. And with that, I'm going to introduce Justin Sharp, who is a senior technical lead at the Electric Power Research Institute, and he's going to kick off our first full panel for the day. Thanks, guys.
All right, jumping right into it. I was thinking Debbie was going to say something before we jumped in, but maybe you just said it. So, okay. Okay, so not a terribly smooth transition, but so weather to grid linkages are really important to this whole process. Paul gave a really good outline. I really enjoyed that talk, Paul. But right at the very beginning, with all of these models, as we're getting more and more weather dependence, the weather data is most important. So I'm going to say a couple of opening words, which I'm hoping are just going to come up. And then I'm going to get right into it because I want to give the panelists as much time as possible. Struggling to advance. Here we go. Okay, so really quickly, I want to just talk really quickly about the reanalysis working group and ERA 6. So two efforts that we were hoping to have Remy Gandoin from who's an offshore wind engineer at C2 Wind in Europe, come and give a little presentation, but I'm going to give a real short one just to go through that. So like I just said before, meteorology touches everything in the grid now. And as we get more and more renewables and more weather dependent load, that connection between the weather and how the grid responds is becoming larger and larger. And it impacts everything within the grid. And I produced this figure over a decade ago, and it's still true today. And you can see really quickly how all the correlations from weather and various different aspects of climate touch the grid. So I don't want to dwell on it too long, just quickly mention this reanalysis working group. So folks in this room who aren't meteorologists have probably used the weather data set ERA 5. It's the most commonly used weather data set. It's what's known as a reanalysis data set. So what you're doing there when you're creating it is you're taking all of the data from all around the world and bringing it into a data assimilation system and then balancing it to a model environment. So it's not actually real data. It's a representation of the atmosphere, and it doesn't perfectly represent the atmosphere. And so back a couple of years ago in April 2024, Remy brought together this team of different people from developers and from the grid and from wind and from solar to talk about reanalysis and how we use it in power system analysis. And that was sort of the genesis of how we got to the WEMC, which is World Energy Meteorology Council, reanalysis working group. And I just want to quickly mention who we are and what we do. So it's a self-organized group that's within WEMC, and it brings together wind, power grid, and marine engineers and scientists with the intent of facilitating collaboration between the reanalysis centers, which tend to be off on their own, and they're not just serving the energy community, they're serving all the stakeholders, and maximizing the value of reanalysis data for the energy sector. So a lot of folks don't know that we exist yet, and I just kind of want to make everybody aware of the group here. So, and the objectives are a collection of user input and feedback, reanalysis validation, which is really important, and we'll talk about it a little bit more today. And then fair and proper use of reanalysis data in wind energy and power system modeling, and then advocacy. I'm going to skip this because I want to make sure I've got time for everybody else. So ongoing projects is we're looking at ERA 6. We're also looking at the MIRA 21C reanalysis data set as well, and doing reviews of those. And really quickly, I want to bring people's attention to the fact that ERA 5 is about to be replaced by ERA 6, which is about twice the resolution of ERA 5. A lot of people are hopeful that it will solve all of our problems. It probably won't. 14-kilometer resolution is not sufficient to be able to represent a lot of the phenomena that occur, particularly with regards to wind energy, but also with regards to solar and loads. It includes a bunch of new height levels which have been placed there in large degree for the energy community to be able to better access different hub heights. And there's a new variable for the Monin-Oberkopf length, which is a measure of atmospheric stability. The plots show basically what the topography looks like in era 5 versus era 6. Actually, I think this is that's topography plot, and I think it's got offshore wind on it. And what you can see is basically era 6 looks like you've put a pair of glasses onto era 5. So you'll be able to represent some of that topography a lot better, but still not as well as you need to. So we did, Remy did a quick analysis of the quality of the era 6 data, and we found that, so the left-hand plot basically shows you that era 5 has this low wind speed bias that we're well aware of, particularly in higher wind speeds. And basically the difference between era 5 and era 6 is not particularly profound. So there's a slight increase in the wind speed. It's got very similar diurnal cycles. So the bottom line conclusion is don't assume that when era 6 comes out, that's going to solve all our problems. I'm going to skip this one as well. I'll quickly say every power grid analysis using reanalysis should contain a reanalysis, verification and validation, and an uncertainty quantification. And we're proposing some classes. So every time you do a power system modeling study, you'll say, my input data from a weather perspective has either been comprehensively validated against quality measurements and the uncertainty quantified for things like diurnal cycle, seasonal cycle, and geographic range, the range of different of the variables across geographic ranges. Currently, most people don't do that because they assume that reanalysis data is representative of reality. And more studies are showing it's not. So we want to also utilize and compare more than one reanalysis data set in our studies. So if you run your study and then just run it again with a different reanalysis data set, you will get a different answer. And I encourage you to do that to see how profound the differences can be. So I'm going to leave it at that and hand it over to my colleague, Carolina Draxl, who also works at EPRI. She's going to tee us up with a talk on enhanced weather-informed transmission planning for this weather to grid linkages. And then Neal Mann is going to follow up directly afterwards with a directly related presentation. So I'll hand it off to you, Karen.
Well, thank you, Justin. Good morning, everyone. My name is Carolina Draxl. I'm a principal technical leader at EPRI in the Energy Systems and Climate Analysis Group. And I'll be talking about the weather to grid linkages that we pursue at EPRI, especially in my group. And like Justin said, I will then tell you how we use these linkages for enhanced weather-informed transmission planning. And we'll show throughout my talk what we hand over to the project Neal is going to talk about next. Okay, I want to start out with explaining how we use climate and weather data as input to electric system modeling tools. And I have here the word consistent because once we choose a data set, we use that same data set through the entire modeling chain. So in terms of climate data inputs or weather data inputs, we use long-term climatologies such as era 5 that Justin just mentioned, climate projections such as CMIP6 scenarios. We take care to use synchronous temp, wind, and solar data, and we make sure that extreme events and variability are represented in the data set. The climate data then informs the asset performance and vulnerability curves. So we want to understand how the weather impacts the assets, like, for example, generation facilities, solar plants, wind turbines, transmission lines, etc. The climate data also inform the load projections, both for historical periods and future periods. And both the climate data inputs and the asset performance information then go into our processes where we do climate risk screening to identify high stress operating periods. All this information is used for our regional policy and tech-economic pathway models and capacity expansion modeling, as well as resource adequacy and production cost modeling. Also, we use this information for transmission planning analysis, distribution resilience modeling, transmission operations, and distribution operations. And all this helps with decisions in planning and operations, resilience investment prioritization, and emissions. And now I just want to show you for a few of these processes what we do exactly. So in terms of climate data inputs, we make sure that the data is hourly. And if they aren't at hourly resolution, we downscale them statistically. And I'll explain later in a talk how we do that. For load projections, we use the geospatial end use model GEM. And that combines a variety of data sources to estimate final energy consumption and emission at the end use level, such as cooking, washing, drying, or at the equipment level. And so that's like space heating and cooling, for example. And that's done at the state or county level. For regional policy and tech-economic pathway models and capacity expansion modeling, we use the US region model. We also have a Canada region and a Japan region. And that helps with simultaneous decisions about capacity planning, transmission and dispatch with hourly correlations between wind, solar, and load. I also want to let you know that we have a new development, which is Stratos, that is a capacity expansion, resource adequacy, and production cost model. It's highly adaptive and yeah, it's a new development. It will come out pretty soon. And last but not least, in the remaining slides, I will talk in more detail about how we do the climate risk screening with our risk tool. So the risk tool combines the weather data plus the asset vulnerability function plus the load projections to identify these periods of high stress in operations. And so I want to also let you know that this tool is open source and available on GitHub. And now I'll go through all these parts of the equation separately. So first, let's start out with the weather data. So as I said, we want to use hourly data, and if they're not available, we downscale, because it is important, like we've heard before, that we get these signals of the hourly weather data for resource adequacy modeling, et cetera. So we start out with historical data. And if we don't have enough of that, we expand that, and then we trend. As a second step, we calculate the quantile-specific monthly delta in daily maximum temperatures between the historical period, which is the baseline, and the projected data, or the data we want to downscale. And then we shift the historical daily min and max temperatures to a future climate year with these deltas that we calculated before. And then lastly, we convert the shifted daily min and max temperatures to hourly data based on the historical diurnal pattern. I want to point you to two publications. The first one was published by my colleague Eric Smith, who is also here at the meeting, that really describes this method in detail. And the second one is a story that talks about how we used this method and it helped inform resource adequacy modeling. So, okay, now we have our hourly data collected, and this hourly data is then passed through the asset vulnerability functions. And how this could look like is that for onshore wind, for example, we can say that if temperature is below freezing and we have precipitation, we can expect a derate of 90% due to blade icing. Or if my wind speed is greater than 25 meters per second, I can expect a derating of 100% because I've reached my cutoff wind speed. Then we estimate the electricity demand based on the weather data with the GEM model that I mentioned. And so the hourly electricity demand estimates incorporate the local weather sensitivity, future technology adoption, energy efficiency improvements, and temporal correlations. And so, yeah, putting this all together, we can identify these high stress operating periods. And I want to show you in this graph how this looks like. So on the x-axis here is time. This is a week long of data. On the y-axis, you have available supply in megawatts. And the colors is your generation mix. So the gray is nuclear. The red color is the gas. We have a little bit of solar in yellow, and we have some wind in this generation mix. The black line is load. And so during some of the time, we see that there's a gap. So load's not met. And this is a high stress situation that we're dealing with. And this is what risk can help with. And you can change these things. You can play around with the generation mix, or you can use new system build outs in your setup. You can add adaptation measures. You can use different climate data sets. Depending on which data set you fit in, you might get slightly different results, especially when we look into the future and climate data are a bit uncertain. You can try things out. You can adjust the asset vulnerability functions to what matters for your system, and we can input also new load assumptions. And so now what we we want to understand is, well, what kind of weather caused that situation? And so this is something Risk can also help with. And I want to show you an example for a week in December 1989. It was a week with we had a cold snap. Here again, we have time on the bottom, and we have this time generation capacity outages on the y-axis in megawatt. And through a clustering techniques, Risk is able to tell us that, in the green and the orange colors, we had low wind conditions. We had no sun, which is the light blue, and this purple is extreme cold. So it was a 3-day cold snap that led to these outages. And in this case, it was 50% of outages. If we contrast this to another week in a different year, in December 1983, this was a 5-day cold snap, so longer. Again, we had low wind, we had periods of no sun, we had extreme cold. It was longer, but it led to fewer outages. And so this is what Risk can help with, and this is what matters, that we understand how the overall system responds to weather. And this is the kind of information we are passing on to the project Neal will talk about in the next slide, or in the next talk. And I just have one more slide here, and it's just to tell you that what I just talked about, the practices and processes we follow and recommend for representing climate impacts in bulk and electric system models was published in a Climate Ready deliverable. Climate Ready was a 3-year initiative that aimed at developing a framework for climate resilience assessments and adaptation planning for power systems. And so we have written this up, and this guidance document walks through the flow of climate data information across the models and processes. And with that, thank you for your attention. If you have any questions, please email me, or we'll speak in the breaks.
Thank you, Carolina. I'll let Neal take over right away. Just a quick note, though, if you ever want to stress test December 1983 or December 1989, make Uri look like a walk in the park.
All right, good morning, and thank you, everyone. So Caroline and I coordinated on the entry part of our title, Enhancing Weather-Informed Transmission Planning. So I'm going to talk about a workflow and case study that we're developing to apply some of these things to demonstrate some of the utility there. So I'm going to talk about this project, and I summarize it in 3 objectives. So what we're trying to do is we want to first identify extreme weather scenarios across multiple historic and synthetic data sets, talk a little bit more about that. Second, create a more robust weather resilient transmission planning process. So that's enhancing the workflow. And then third, demonstrate the economic and reliability benefits of that new planning process. So that's the project objectives in a nutshell. So this is a combined team. It's a great team between Argonne and EPRI. So Todd Levin is our PI, and Carolina is on the EPRI side of the team here today. And then we're getting our funding from DOE, Office of Electricity, and support from the Office of Critical Minerals and Energy Innovation. And our program manager, Cindy Bothwell, is in the back. So thanks, Cindy, for your support. So I try to distill this down into very simple charts here for the audience. So the first step on this is sort of the front end of the project, right, is the weather data. So we've got 2 different data sets. I color-coded: red is Argonne and blue is EPRI. So we start on the left with what we call the Argonne ADA2 data set, and then EPRI's QDM data set, as well as ERA5 on the front end. We take those, we translate them into load, PV, and wind generation in the weather to grid step in the middle. And then once we've created grid relevant time series, then we're looking for the hazardous periods with a couple of different methods. One of them uses the risk screening tool from EPRI. One of them is an Argonne developed in-house called Hazard Index. We combine that with representative periods when we're doing our capacity expansion. And then all of that goes into this violet box on the right that I like to call the super ensemble grid data. So that feeds in to another step that I'll show in a minute. So let me talk a little bit about the weather data sets. So ADA2 is short for the Argonne Downscale Data Archive version 2. It's a dynamical spatiotemporal downscaling data set. So basically, we took ERA5 as boundary conditions. We also then looked at 3 different GCMs from CMIP6 over the North America domain. So we used WRF, and by we, I mean our atmospheric scientists. So this is Chenyang and Jolly in particular, to downscale that to about 4-kilometer spatial resolution, hourly temporal resolution. And they were able to enable convection permitting, which is an important feature that's not commonly done. So out of that, we've got about 80 weather year scenarios, both historical period and synthetic mid-century data set. On the EPRI side, so we're trying to call it QDM shift now, so quantile delta mapping. So Carolina talked a little bit about the technique. It's a statistical temporal downscaling, so taking the ERA 5 historical data and then doing all the shifting that she showed over North America. So it's got a little bit coarser resolution, same as ERA 5, but hourly temporal resolution as well. But they can create many more weather year scenarios out of that because it's much faster. You don't have to use the HPC time to run WRF. So basically between ADA2 and QDM shift in ERA 5, we have 3 different data sets that we're trying to look at in a coherent way together. And basically at the bottom, I wrote, our hypothesis is if we leverage both historical and synthetic data and 2 different downscaling techniques, then we can better characterize the uncertainty in the weather and provide better, more robust assessments downstream from that. So this is an example of some comparisons and things that we've found so far. Justin mentioned the known ERA 5 negative wind speed bias. So this is kind of an example. ERA 5 on the right, ADA2 downscaled, ERA 5 on the left. So this is an annual mean wind speed for 1 year. So you can see that the annual mean wind speed actually with the ADA2 downscaled data set is a little bit higher than ERA 5. So it does not fully correct the negative bias, I'll just say. If you compare that against observational data, and we've done that at several points, it's still a little bit under, but it is better. But when you translate that, of course, into wind generation, those differences are amplified. So with ADA2, we're getting much higher wind generation output than you would if you were just using the ERA 5 data set unbias corrected. So that's a potentially important distinction and difference between the data sets that we're trying to understand the implications of. So that violet box from before, our super ensemble grid data, feeds in here to a step where we basically do some sanity checks and validation on a generation expansion plan that was not developed with these weather inputs in mind, these weather scenarios in mind. So we're going to take an externally developed generation expansion plan, downscale it. So our kind of current working resolution is county level for ERCOT. So once we downscale it, we're going to take in the weather from the super ensemble, run through the risk screening tool, find some hazardous periods, and then run a reliability assessment step with our ALEAF tools, and then find how much unserved energy is there, calculate some of the reliability metrics, see if they meet what our reliability criteria are. If they don't, then of course we have to go back and we need to make some corrections, add some capacity until we meet those metrics. So we're basically trying to correct the generation expansion portfolio for these hazardous and extreme weather events before it goes into the transmission planning step, which is the whole point of the project. So we got to get a resource adequate and reliable generation expansion plan first. And then that goes into this final step of the transmission expansion plan. So we got 2 different sides to this, fairly traditional economic evaluation on the left and the steady state AC power flow kind of analysis on the right. So we've got, the Argonne team doing one part of this, EPRI team doing the other part. And then we're going to look at it together in a combined all solution weighting, check, what things are different. So one of the main, takeaways that we want to give in this case study is if you add these additional weather scenarios, if you add these hazardous and extreme weather periods, how does that affect the transmission plans that come out of your study? So far we've extracted about 3 terabytes of weather data. We've got several more terabytes in the works. We've done about 40 of our scenario years conversion into grid data so far. The risk team has expanded their resolution. So we're aligning this to counties in ERCOT. ERCOT is our case study, and we've identified some initial hazardous periods out of the data sets that we've done. We've validated the synthetic 7,000 bus ERCOT system for the power flow studies. And then we've got a few different things in progress here that's going on. So that's kind of the end of my talk, and thank you for your attention today.
Okay, moving right along. Next, we have, and Ilya, I apologize if I murder your last name, but we have Ilya Chernyakhovskiy, is that right? Who's going to talk about load forecasting for a structurally uncertain grid.
Hi, everyone. Okay, got it. So I'm taking a slightly different approach here, and I'm not starting with weather, but I'm starting with load. So I'm going to talk about the shifted load forecasting paradigm that we're seeing. I'll motivate that a little bit. I'll talk about an approach we're taking to have a data-driven approach for forecasting large load additions in the medium, sort of short term. We'll talk about data centers in the hourly dispatch stack, and that's really where I'll get to weather and the impacts of weather. And most of my talk here is motivating the work ahead that we have within the lab, but also in the industry as a whole. So as a bit of a motivation, we're seeing that the load forecasting problem has shifted, so we're really in a new paradigm. The chart on the left here, so you see the blue lines, those are historic EIA load forecasts looking out to 2050. All of the blue lines are the forecasts starting from 2015 up to 2023. And then you see the shift where the red lines, those are the latest EIA forecasts from 2025 and 2026. So by the end of the period in 2050, you see a 20% shift or an increase in the total load for the US. If we zoom in to Texas, so the ERCOT example here, we see this is even more pronounced. So we see the structural shift in the load forecast in certain scenarios. One of the scenarios that the PSU is evaluating are these unfiltered interconnection requests from large loads. So data centers, we really see that driving a lot of the uncertainty across the scenarios. So if you look across different historic load forecasts, we see this really wide range, up to 4 times the current peak demand. And we see the spatial distribution of these new large loads is really varied as well, right? So this chart on the right, it shows the planned and sort of announced data centers in Texas. And you can see some really big projects that are under construction, but there's still significant uncertainty about how they will operate on an hourly level. What are the technologies for cooling? How will those cooling technologies respond to weather events like heat waves? So that's really what's motivating a lot of our work. And we're asking, okay, how do we represent this in grid models that need to represent load at a very high level of fidelity for us to get the transmission and generation planning right? So one approach we're using for sort of that near-term large load projection is to add probability distributions to these key areas of uncertainty. So one of the areas is materialization. Will a facility that's announced or planned get built or not? And so we can do Monte Carlo sampling across every facility and different probability weights on based on the phase of construction or the phase of planning for that facility. And then for facilities that are built or that are selected from our sample, we have a lot of uncertainty in their operations. And so 3 key areas that we're creating probability distributions around are utilization. So you can think of this as a capacity factor for the load. The cooling overhead or the power usage effectiveness, which is a term from the data center industry. So how efficient are these cooling systems relative to the IT loads? That can vary dramatically depending on the cooling technology that's used. And can really impact the overall annual load, but especially during heat waves and periods of really high cooling needs. This parameter can be really important for understanding what the load is that the grid needs to serve. And then the peak to average ratio, you can think of this as kind of the variability of the utilization of the facility, right? So if we sample across these parameters, both materialization and operational uncertainty, we do a Monte Carlo study to create these ranges of potential outcomes in Texas based on the projects that are announced. We get a range of 20 to 70 gigawatts of peak demand by 2028. You see this level off, which is really why I'm focusing on the near term and kind of short term forecast here, because this really depends on the projects that we know about, right? So that we need other methods to forecast further out, to create synthetic facilities, understand where they would show up on the grid, and do scenario analysis on what those loads will be. But in the short term, if we look at the county level and we zoom in, we see that based on the announced facilities, peak demand in these counties can either double or triple. And this is in a kind of median P50 scenario. And there's one county in particular, Carson County in Texas, where you see this massive range of possible outcomes in the load. And this is driven by a single facility, right? So there's a single facility that will drive how the grid needs to operate and how the grid needs to develop in that part of Texas. And so the probability of that facility materializing and how it operates will really drive our grid planning decisions. Okay, so what's one of the next steps, and part of our ongoing work right now is going from peak demand assessments to the hourly load profile of these facilities. We know that these facilities don't have a flat load profile. You know, that was kind of a good starting point for modeling these in our grid models, but now we have better data. So Robbie Vercellino and team from the lab, they published these facility level power consumption profiles for different types of data centers. Here I'm giving an example of a 10 megawatt co-location data center. This is based on work that they've done with the high performance computing that we have at the lab, so simulating AI workloads. And so they've captured the IT workloads and their hourly profiles over a year. That data is available on the link I have on the slide. But what we're missing right now is the weather impact. So the cooling demand and how cooling changes when you have different weather throughout the year. And at the same time, how you have cooling demand during these really high or low IT loads. Sorry. So what we really want to get to for our grid modeling are these 8760 weather correlated data center cooling loads, so that we can include that in our hourly load profiles. We also want to be able to represent extreme weather events. But to get there, there's a lot of upstream work that is ongoing that we need to finalize and publish before we can get to that fully resolved grid planning decision on how to meet these loads, right? So we need to understand where the loads will show up, what is the transmission capacity, the headroom to meet these loads. We need to understand their behind the meter generation systems and how those will operate. Will they be purely for backup capacity? Will behind the meter resources be running to serve local demand at the data center? And if that's the case, we need to model that explicitly in our grid models. We also need to understand their flexibility, right? So what is the potential for IT loads to shift when you have grid stress periods, or when you have a heat wave, for example, that's going to impact our understanding of their loads, especially if you have correlation between facilities that have the same owner. And that can really adjust their IT loads and mitigate impacts on the grid. Okay, so a quick takeaway, kind of to summarize. We can see that based on near-term projections, the data center can swing total load, especially if you look at the county level, from 2 to 10x within the same planning horizon. So whether the facility shows up or not is really what we're concerned about in grid planning. And then weather precision on a wrong baseline is false precision, and that's kind of the challenge that I would pose to the panel. Thanks.
Thanks, Ilya. This is a topic that I hope we're going to explore a little bit more in the panel question section because it's really fascinating. Next up, we have Priya Sridharan, who is Senior Program Director at GridLab, and she's going to talk about leveraging weather data sets for resource planning in India. This is a project I was involved in too.
Great. Good morning, everyone. Thank you so much, Justin. Really excited to share a bit about an ongoing effort that GridLab and RMI have been leading on resource planning in India. We've brought together a really amazing consortium on this effort. It includes Tata Power, who was really the catalyst for this effort, Vaisala, EPRI, National Laboratory of the Rockies, and EDS, which is a consulting firm based in India. I wanted to spend a few moments on the context, which I think my fellow panelists have done a really great job already getting into. So while understanding the impacts of weather has been a focus in the US, it is also of great interest and importance in countries like India, which have goals for building non-fossil based capacity. As my fellow panelists have discussed, having good quality data is really integral to doing this kind of analysis. And unfortunately, the quality of the data is arguably lacking everywhere. But I would say in India, particularly in terms of granular data sets, that is still an emerging area. However, as my panelists have spoken about, the evolving best practice is that we do need to pay attention to things like having weather coherence between both our demand and our generation in order to do planning well. So against that context, the goal of this effort has been to develop various portfolios or paths towards meeting 60 to 80% clean by 2040 and understanding what those economic and reliability trade-offs are between different resource choices. This effort really goes beyond just doing a study. One of the things that excites me most about this is about doing this work, developing these data sets, making those publicly available, both in terms of renewables, as well as weather data sets, the granular weather data sets, as well as load forecasting. The modeling framework is a fairly straightforward one, from load forecasting, multiple different pathways of load futures, developing resource portfolios using capacity expansion modeling, then testing multiple portfolios in production cost modeling against multiple weather years. We've had a lot of discussion on that. And then in the final step, going even further and sort of asking these what if questions and doing grid stress testing. In the industry, some of us have been talking about this in terms of stress testing, but it's really sensitivity analysis. I did want to spend a few moments on why we're taking this approach as opposed to doing probabilistic RA analysis. And the pyramid on the right explains it, I think, in visual terms. So at the base of the pyramid, the goal is to evaluate multiple portfolios, which may represent different load futures in a production cost model for multiple weather years. And that allows us to really understand what that risk is due to interannual weather variability. Then at the middle of the pyramid, what we're doing is asking these sort of what if questions and evaluating what may happen if we have particular grid stresses. We can even evaluate things like anti-stressors, like load flexibility or demand response. We can test these in combination or in isolation of each other. And then at the very top of the pyramid, we have probabilistic RA analysis, where all of us know who do this work. You're taking one portfolio at a time, one load future at a time, and then really digging deeply into the impact of forced outages. In this study, all of these components are useful, but in this study, we're really focusing on the base of the pyramid and the middle of the pyramid. And I would argue the further out you go, the more important it is to prioritize going in the sequence from bottom to top. This slide summarizes some of the key weather to grid elements of the project. So developing granular weather data sets, as well as aggregated renewable shapes for multiple years. 10 years is what we've gone with. That was a core objective We've actually released those data sets already. They're on our website. There was an accompanying webinar that was held in September 2025. Second part, as I mentioned earlier, is really emphasizing that aspect of developing weather coherent load forecasts. And I'll get a little bit into this more later, but we've utilized both a combined bottom-up and top-down modeling framework. And as I mentioned, evaluating these portfolios and production cost modeling for multiple weather years. So we worked with Vaisala, who I think is actually here. And I apologize, I meant to also mention that both Justin and Ilya have been an integral part of this team. So we do have a wonderful team. We worked with Vaisala, whom everybody knows here, that has great skill sets on doing this kind of developing simulated data, downscale data. We developed 10 years of wind data, 5 kilometers, 15 minutes, and that was using numerical weather prediction modeling, WRF model. That light validation was also done. Those data sets are online. And we also worked with Vaisala to develop solar data sets, and that is primarily based on satellite-based data. There are a lot of details on these methodologies, as well as actually we published the question and answers that came up during the webinar. So I encourage you, if you're interested in learning more on this dimension, please visit our website. That also contains a lot of details on what I'm showing on this slide, which is that you can't really do much with the 5 kilometer data if you're trying to develop portfolios. That's a lot of data, terabytes of data. We worked with NLR to convert those raw weather data sets into usable renewable shapes for all of those weather years for 147 regions in India for different renewable technologies. We've also been undergoing a validation process with Tata Power as well, using a tool from one of our national labs, PNNL. So I'm giving you a bit of a whirlwind of the study, and the study is ongoing, but I did want to show at least one illustration that is a draft illustration, but I think really sort of highlights some of the things you can learn from doing this multiple weather year analysis. So this is one of our 4 portfolios, which was designed to a 60% clean target by 2040. And what we've done is for each weather year, we're showing what the percentage of daily demand is met by variable renewable energy. The gray dots are the daily markers, and then the blue dots are a 3-day rolling average. And with this kind of analysis, you can see things like, you know, what are the periods where you're having consistently low RE generation? And in this case, we're seeing a pretty consistent pattern of that occurring in the October to December timeframe. Although I haven't showed this, we've also done this comparison across other portfolios, and you can see things like, you know, how much more variability do you have if you have less wind versus more solar, et cetera. So that kind of analysis falls out when you do this sort of comparison. So I wanted to switch gears a little bit and move over to the load forecasting piece. As I mentioned, a big goal was to develop weather coherent profiles. We've leveraged a hybrid top-down, bottom-up approach, which I think is really essential if you are trying to capture emerging trends that aren't really reflected in the historical record. In both cases, we are leveraging historical weather data sets, but the bottom-up modeling was really done to capture trends like electric vehicles, as well as a dramatic increase in adoption of air conditioning. So this goes into a little bit more detail on the bottom-up approach for modeling the cooling load. So this is where we worked with EDS Consulting, which has the expertise in building energy simulation modeling. And what we did was create load shapes for representative buildings across different climate areas, climate zones in India, for actually adopting different levels of energy efficiency as well. We took those normalized shapes, we applied stock values, and then aggregated those up to the state level. So this has some analog to the kind of simulation work that was done in ResStock and ComStock, if any of you are familiar with those tools. So this is the kind of result you can get from doing this kind of analysis. So what I'm showing is for 5 different states, what the residential cooling load projections look like for 2030 on a sample day. There are 2 trends that are interesting when you look at this figure. One is the difference that climate makes, which is indicated by the different colors. And then obviously in all of these, you can see what the hourly sort of pattern looks like for cooling load usage. You can also see the impact of the different weather years by comparing the solid and the dashed lines. So I'm going to actually wrap up, and I wanted to summarize some of the insights so far on this effort. As I mentioned earlier, doing this sort of multi-weather year analysis can be really helpful for planners if we're trying to understand what are some of the consistent trends across weather years that we may see, can help us identify periods like low RE generation as well as curtailment risk. We did have some conversation earlier in the panel about how it is ideal to have a consistent source for your weather data sets. We weren't able to do that. We did rely on satellite data for solar and NWP for wind, and actually a different data set for the load forecasting, which was ERA5 land. But in some cases, that might be unavoidable. We brought the best data sets that we could find for that particular component of the analysis. Lastly, our hope is, this is only 10 years of granular data sets that we've developed, and obviously that's not going to be sufficient moving forward. But our hope is by making these data sets available publicly, and also sort of demonstrating the value of some of these frameworks, that other practitioners and researchers based in India and elsewhere can really take those forward. So with that, I will end it. And yeah, feel free to reach out if you have any questions about this effort. Thank you.
Thank you, Priya. Last up, we have representation from a major system operator. So Ryan Kelly is with us and is going to talk about load, weather, and renewables in probabilistic modeling. And then after that, we hopefully will have a robust Q&A session.
Yeah. Good morning, everyone. So Tim here to review basically the MISO load development process and some of the recent updates we've made to our wind profile development process. And some of those key takeaways, we use 30 years of weather data for both our load profiles and our wind profiles. And we've made updates recently to our wind development. So let's just go into it. The major components of our LOLE probabilistic study, you can see the green ones there, the ones that I'm going to partially talk about, load and renewable. But there's dispatchable capacity. That's one of those in there, also affected by weather. Non-firm imports, be affected by weather. Obviously, cold weather outages affected by weather. So it kind of touches every single aspect of what we do. Now, for our load development process, the first step is obviously gathering the temperature and load data. Now we use 30 years of weather data, and we'll gather the previous 5 years of load data. I've adjusted these graphs a little bit. There's not really that big of a difference from year to year, but if I put it what it actually is, you can't really see anything. So you can kind of see, that 5 years based on temperature where they fit. After that, what we're going to do is MISO has 10 different LRZs. That's where our zones are. For each of those, we're going to use that 5 years of load, and we're going to scale up the last 3 years up to kind of match the most recent 2 years, so that we get a 5-year representative sample of the way that load has been performing in those temperatures in that LRZ. From that point, once we have that 5-year hourly load for each of the LRZs, we're going to do a regression analysis. And that is to get that kind of correlation between the temperature and the load in that LRZ. Right now, we use a neural net process in order to get that regression. We've been evaluating different ways, that we could speed it up, do some more automation, things like that. From there, once we have that connection, in step 4, we're going to create that 30-year hourly load profile per each LRZ. And so the step 5, this is one of the interesting ones. And in that graph, we kind of chose, I think, the worst performing one. But obviously in the 5 years you're going to be using, not every temperature that you've seen in the prior 30 years is going to appear in those 5 years. So that can kind of, introduce some errors in the regression analysis, especially in those extremes. So if you see some of those little blue cutoffs, this is the most extreme example we have, but that was the predicted from the neural net, was that blue, and it kind of cuts off. So we have an extra step where for those most extreme temperatures that don't appear in the 5-year set, but appear historically, we use more of a linear regression fit to scale those peaks up. Because in the end, what we really care about is how well these profiles match reality, so that we can get, representative performance from, the resource class and how will we actually perform in those times. The last step is, it's just more of a timing factor, the scaling to forecast. So we're getting this load information from our members in November. And then the next year, earlier in the year, is when we're developing these load profiles, but we're not. Then we'll be running the study, which is for the following planning year. So they're kind of dated by that point, the forecast that we get from our members. And so this step is essentially to scale it up to what that forecasted would be for that year. Now, where do we use this? This is our iteration framework. So there's the weather years. So we have 30 of those. And then we use a load forecast error. So those are the different load buckets there, positive 2% load or negative 2% load. Each of those has a probability assigned to it. So we've got 30 weather years, 5 times each of those is 150 different load forecast scenarios. And we run 50 Monte Carlo simulations on each of those. So you kind of get to 7,500 random draws in the scenario. So we're trying to really test through a wide variety of temperatures, different capacity that's there at the time, some uncertainty in the load, to really test out and see, like, okay, how well does our capacity fleet perform given this variety of load samples? And that's drives the results that we give to our members as far as planning reserve margin, accreditation for capacity, which I'll touch on a little later with the LOL. And that's very quick, our load process. And then the wind profile part, as was kind of briefly touched on, we use ERA 5 as well, with that 100-meter wind speed. That's our primary input. We use the data since 1995 to get that 30 years back, and it covers our entire fleet with a 31 by 31 kilometer resolution. We also use our historical wind fleet generation since 2012. You'll have their capacity, location, but we also factor in manual redispatch if it was curtailed, and maintenance in order to get a more accurate representation of that wind's performance. So what we did is, for every individual wind farm, we used a training/regression to essentially create a power curve for every single wind farm, factoring in the hub height, cut in and cut off speeds. And then we would aggregate those results to a zonal level, again, for the MISO 10 zones, in order to create 10 different zonal profiles. Now there's a different process than we did, but we also, we took some steps to validate, how well does doing it this way perform. You can see there's the blue chart there is a mapping of the actual capacity factor versus the regression capacity factor in 2012, which is a year where we had both performance data and so it's kind of the latest year to see how well did it perform. The zonal fit results there, you can see pretty good R-squared values and root mean square values. And then we looked at it obviously on a time series factor too, because we want to see, is the performance of the regression matching pretty well the actual. And then the really important part for us, identifying and validating wind routes. Because in the end, what we're trying to do is identify when is the risk happening. And so this is one we're showing the regression versus the actual between one of those wind route times, which was July 19th to 24th in 2024. And you can see there that it does identify it, but you can also see that there's areas here for improvement. So The red is the regression, and it is pretty consistently above what the actual was. So, there are areas to make more improvements. Is it cut in speed? Is it granularity on where they are located? There's different things we're looking to better address those. And so the wind accreditation, this is where it all kind of leads to for us, is how do we accredit this generation? Well, how do we model it correctly to identify the right risk periods? And then how do we properly accredit wind generation going forward? So currently we use effective load carrying capability. We'll use that for the next planning year, just 27, 28. And that's more or less just evaluating how reliable is our system with and without that resource. Now, the future, which is 28, 29, we're changing our accreditation model to what's called direct loss of load. And that is essentially to treat every resource kind of the same as far as how we accredit it. And that is by looking at how well do they perform during critical hours in our LOLE model. So when is the system the most stressed? When are we having loss of load hours? We weight those based on their probability to get a class level performance. So it becomes very important getting these inputs correct, because if you have bad inputs into the wind speed or the performance on the wind generators, you're going to have bad outputs in terms of accrediting those generators. And then you're just kind of going to lead into reliability issues down into the future. Our accreditation model, that second piece on the right, the darker one, there's still a deterministic part. So while our LOLE model will give them a class accreditation based on how well they perform, given that array of 30 years, they do still get a chunk of that piece of the pie. So wind could be scaled down to whatever their class is. How well those individual resources perform determines how much they get of that pie. So we still want to incentivize them performing, not just giving them out of the model and how we say they'll perform. Challenges, next steps. Obviously I talked about, we have to improve representation of those high impact weather conditions. Heat waves, cold weather events is another one we're working on, because those are the things that are driving the riskiest periods. And so those are the things we're trying to model the best, so that we get the best accreditation, so we get the best results in terms of reliability. And then improving meteorological data. Ideally, more granular data will give us, better accuracy. Any other things that we can go through. So that's all I kind of have. Hopefully I went through it pretty quick for you all. Thank you.
All right, going to move into the Q&A. I want to invite the audience to move up to the microphone to ask any questions. I have some seed questions which I'm going to give to begin with, and I'm going to start off with a relative softball, which is going to go to particularly to Carolina and to Priya, but I think everybody on this panel might have an opinion and something to provide around this. So there's a lot of data sets that are out there. Which ones would, if you had to choose, which ones would you recommend that we use? And